In this video, we're going to practice our skills drawing Lewis-dot structures by looking at carbon dioxide and also the cyanide ion. Let's do carbon dioxide first. All right, so carbon dioxide has this structure. Okay, and always the first thing that we do is just count the valence electrons of each of the atoms and find the total number of valence electrons. Okay, so carbon is a 2s2, 2p2, so that is 4 valence electrons, and then oxygen is a 2s2, 2p4, so that is a total of 6. You have 6 plus 4, 10, plus 6 is a total of 16 valence electrons. Okay, now when we draw these bonds, we've already used 2 electrons per bond, so there is a total of 4 electrons in constructing the single bonds between the carbon and the oxygen. Right, so the leftover will be 12 electrons after we form those single bonds. The next thing that you do is you take the leftovers valence electrons and then you place them as lone pairs in the terminal atoms first. Okay, so the terminal atoms are going to be oxygen, right? So we have 2, 6, 8, 10, and 12. Right, so what we've done here is draw 3 lone pairs, so 6 electrons, to complete the octet of that oxygen atom, and we've done the same for the other oxygen atom, and then we find that after this there's actually no valence electrons left over. All right, so now all of the electrons are in play. We have to make sure that every single atom in the structure satisfy the octet rule, unless there's hydrogens, for which we only need 2 electrons. All right, so we see that the octet is satisfied for oxygen and oxygen, but notice that we're missing 4 electrons for that central carbon atom. Okay, so one way to do it would be to say, well, I can take these 2 electrons, and instead of having them as lone pairs in the oxygen, then draw a double bond right there, and that would actually help. Okay, because now you have that the octet is dissatisfied for this oxygen atom, and then you're closer to the octet in that carbon atom. Right, so we still have to find the octet here, so we need an extra pair of electrons. And you now actually have a choice. Right, the idea here would be that, well, you can take that lone pair and add it there as a triple bond. Okay, but that would seem to be unrealistic, because we know that the bonds in CO2, the 2 CO bonds are actually exactly the same. Right, we don't have a bond that would be triple and a bond that would be single. Right, we actually know that both bonds are the same. That suggests then what happens is that one of the lone pairs that you have in that oxygen atom actually goes to form a double bond with a carbon atom, and now you do satisfy the rule. Okay, the alternative structure that we actually have drawn would be this, okay, which we have discarded because we know from experiment the 2 bonds in carbon dioxide are the same. There's actually another argument that we can use to discard that structure with respect to that, and that is the argument of the formal charge, but we're not going to be talking about that just yet. We will discuss formal charge in a couple of videos. Right, so that is CO2, and again the final structure that we have is this one, where you have that every single atom satisfies the octet, and it results in a double bond between carbon and oxygen, between the 2 connections that you have in carbon and oxygen. Right, so that is our first example in this video. The second example is going to be the cyanide ion, which is this, CN minus. Right, so as always, we start by first drawing the molecule, so CN. Here you don't have a central and terminal atoms. Both atoms are terminal or central. And then we count the number of valence electrons. All right, so we go to the periodic table and find that carbon is a 2s2, 2p2, so 4 valence electrons. Then nitrogen is a 2s2, 2p3, that would be 5 valence electrons. And something important here is that we actually have 1 extra electron that we also have to take into consideration. Right, so the total number of electrons would be 4 plus 5 plus 1 is a total of 10 valence electrons. Okay, so then we draw the first bond between carbon and nitrogen, and that leaves our electron count in 8. And then we take these 8 electrons and then place them around the terminal atoms, which in this case could be either. I actually have to choose this. I can choose nitrogen or carbon. It makes more sense that I choose the most electronegative atom first, which in this case would be nitrogen. Okay, so if I start placing electrons for nitrogen, there will be 2, 4, 6. That will complete the octet for nitrogen. And I still have 2 electrons left over, so I can put them here in carbon. Okay? And again, we know that all this has a negative charge, which we can write down as simply brackets with a negative sign on top. All right, so after that, we're done with all of our valence electrons. There's none left over. And then we have to figure out if this structure satisfies the octet rule or it doesn't. For nitrogen, it does, but for carbon, it actually does not. All right, so the way that we do that is by taking lone personal electrons and then finding and making multiple bonds. Okay, so we can take that lone pair in nitrogen and write that as a double bond. And in this case, we see that we still have the octet for nitrogen, but now we have only 6 electrons around carbon, so that's not enough. We can take that lone pair and then make that bond a triple bond. And in this case, we do have that the 2 atoms satisfy the Octet rule, right? So that would be the Lewis dot structure for the cyanide ion, in which you have a triple bond between the carbon and the nitrogen atom. All right, so in this video, we've tried to improve our skills drawing Lewis dot structures by looking at the carbon dioxide and cyanide structures. In the next video, we're going to introduce the concept of resonance, and then a couple of videos from now, we'll introduce the concept of formal charge.